Hello everybody, I'm back. I think this is actually the final lesson of brand new material to be included in this course. Obviously it won't be the last video because we've got warm-up quizzes, we've got mock tests and things to prepare you for the AP exam, which they just released a bunch of really good information, including the test dates this morning, so that's kind of exciting. But this last piece of material is actually not about series. This is going to be something completely different. It's going to be related to a unit we taught at the very beginning of the year, but for whatever reason I've never included it in that very first unit, probably for the sake of time, but mostly just because it didn't feel like we were ready for it right at that moment. It just kind of didn't fit anywhere perfectly in the way we construct BC. Having said that though, it's a really neat topic. It's a pretty rich one. It's one that's very simple, and it'll be grounded in some intuition that you already probably have. In fact, that's what this first page is going to be about. More than that though, I just want to make sure that you're comfortable with it, because it's the kind of topic that absolutely could show up on a modified AP exam, or if you're watching this from a future year, obviously it will show up. It's a great skill, and it's something that's specific to BC, a numerical solution to differential equations. So having said that, other than that, yeah, I think that I'd just rather focus on math today rather than talk about anything else that's sitting in my head. So with that said, let's go ahead and jump in here. So to kick things off, the name of the lesson is Euler's method. We are going to be demonstrating Euler's method and showing you what that is, what it does, how it's beneficial, what value it might have, and then giving you plenty of examples as well as a couple problems to try on your own before working on a problem set. I'll probably reconstruct that problem set before you do it, but I don't think anyone's rushing to get to the last official problem set of the course. So having said that, where I'm beginning here is kind of in an interesting place. It might not seem worthy of a lesson for us here, but in fact this simple concept is actually going to form the basis of the new one that we addressed today called Euler's method. So right here in this first question it says write the equation of the tangent line to the particular solution of 2. Oh geez. Well, you know what, just because I can, let me just get rid of that really fast. Let's see. Let's just get rid of the word 2. So write the equation of the tangent line to the particular solution of dy dx equals 3x over y squared that passes through the point 2, negative 1. Then use the tangent line to approximate y equals f of 3.5. So having said that, basically this is a question you've been able to answer since Calculus AB. There's nothing super intense about this. In fact, it's usually part A of a big extended free response question focused on differential equations and separation of variables. There's no separation of variables here though at all, so let's just kind of work our way through it. To kick things off, if we want to write the equation of a tangent line to a particular solution to a differential equation, of course our tangent line is going to require an ordered pair, which would begin with our ordered pair that they gave us. This is our x sub 1, this is our y sub 1. Now having those two isn't enough for a tangent line in themselves. We also need a slope. But we can compute the slope by taking our dy dx, our differential equation, and evaluating it at that ordered pair we were given, because dy dx, or differential equation, is just a prescription for slope. So in our case here, we just plug that point in. We'd have 3 times 2 over negative 1 squared, which is going to be equal to 6. So that is our, if you prefer the letter M, if you prefer the letter M for your slope, then that's our slope. That's the slope of the line. And in fact, from here we can now construct our tangent line, which is going to be y minus a negative 1 equals 6 times the quantity of x minus 2. So that answers the first portion of our question. Truthfully, as exciting as it is to write tangent lines, that's not really what Euler's method is all about. It's not, yes it is, but it's just kind of the start of Euler's method. Really, the idea that really brings out Euler's method is the second part, that asks us to use the tangent line to approximate the value of the function. So underneath here is a concept that has a couple different names. I believe we called it local linearity, that's a good name for it. I'll explain what I mean by that in just a second. If not, the other term I might have called it, just depending on the year, I don't recall which one I used every single time, would be just linear approximation. In a sense, I'd say more like local linearity is the idea that leads to our ability to do linear approximation, but the idea is the same. What that means is what we want to draw out of here is the idea that our tangent line, which is going to be 6 quantity x minus 2 minus 1, if I just subtract 1 from both sides, that equation is going to be a good approximation of f of x when we're around the point of tangency. So specifically when we're around the point 2, -1. So when we're in that neighborhood, that tangent line will do a good job. Here, I'll show you what I mean Desmos-wise. So if we look up here, here's the solution to the differential equation. Don't worry, we'll get there later. Our ordered pair is right down there, 2, -1. The idea of this concept is that the tangent line, which I think we had y plus 1 equals 6, quantity x minus 2. That tangent line and the curve itself, when we get really close to the point of tangency, those two things look very similar. In fact, if we're looking at this from our series perspective, you might even want to say something like, it looks like as we zoom in, the two converge. The tangent line and the curve end up seeming the same. In truth, they're not really the same. They just look very similar because the closer we get, the more linear the behavior is. So in other words, that means the tangent line is a really good approximation of the curve when we're in that area around the point of tangency. So that's what we're saying here. We'll use the tangent line to approximate the function at some value that's near the point of tangency. So for us in particular, we want, it looks like f of 3.5, that's what. We want f of 3.5. So that means we're just going to plug in to the tangent line. So in other words, f of 3.5 is going to be equal to our tangent line with 3.5 plugged in. And when we simplify that out, that's 6 times, this is going to be 1.5, so 3/2. 18/2 is 9, minus 1 is 8. So what that says is our linear approximation says that f of 3.5 is approximately equal to 8. So again, that's a lot of work for a problem that you've done before, and you're probably sitting there thinking, okay, cool, nice and comforting, very straightforward, but why did we spend time doing this? The reason we spent time doing this is because, surprise, you actually just did Euler's method. You did the simplest first, what's called iteration of Euler's method. Because what Euler's method is going to do is it's going to take the idea of linear approximation and using a tangent line to approximate a function value from a differential equation. And it's just going to do it a few more times. You're just going to do it more often. You're going to recalculate, create new versions of tangent lines, or pseudo-tangent lines might be a more appropriate way, and you'll use that to approximate your value. Think of it as like doing multiple tangent line approximations one after another using results. The process will be what's called iterative, meaning you're going to do the same thing over and over again. You're just going to keep shifting and slowly approximating the value itself. So that's a lot to take in. Let me show you what I mean visually before we dig in too far. So what I have here is a, well, first of all, a picture. I'm spoiling things. The truth is, like, I don't want to spoil that just yet. We'll get there. So from here, what we're looking at is we're looking at a picture of some solution curve. That's what we can call this right here. We'll call this some function f of x. Like, we'll just say, well, yeah, we'll say that. This is some particular solution f of x. So we're looking at values of f of x. You know, maybe the graph's right over here. Who knows? That's not my goal. So the idea is, with f of x, what we just said is that we can approximate values of f of x by using the tangent line. So for instance, if I draw a point right there, and I say that's my point, I don't know, let's say that it's at x equals 2, since that's what we did in our first example here, then what linear approximation says is if you sketch the tangent line to the curve at that point, you can go over to where 3.5 is, and you can create an approximation. Actually, let me do this. You know what to do. So if we go over here to 3.5, we can approximate the value of 3.5 right up here. So this would be our approximate value of f of 3.5. So there is the approach that we use with linear approximation. One tangent line, we get everything right there. The problem with this approach, as you can probably see just from looking at it, is that there's a sizable error that occurs right there. Let me make sure I'm using the correct notation. Yes, I am. There's a sizable error. Obviously, there's a difference between those two. It is just an approximation, so we weren't expecting a correct answer, but we'd like to be a little more accurate where possible, at least as much as possible for a given solution curve or differential equation that we're modeling a solution curve for. So here's the idea of here's the idea of Euler's method. Euler's method begins the exact same way. So of course I have to draw another tangent line, and I'm not so good at drawing lines. Yeah. There we go. So there's where we begin. It starts with 2, and obviously our ultimate goal is to end up in the exact same place and get an approximation of 3.5. What Euler's method is going to do, though, is instead of continuing forward with this tangent line like we did before, and then doing our approximation up here, what Euler's method does is it stops at a certain point, and it recalculates a new tangent line. Now, it's not a true tangent line because it's not going to necessarily touch the curve at all, but the idea is we can model the growth and rate of change of the solution curve by constantly recalculating the slope at points using the linear approximation. So the idea would be maybe we'd decide to split it up so that going from there to there we'd go at 1/2 or 2.5, and then we'd probably go one more step and go somewhere like 3. And so at each of those points, we would use a value that's approximated, a y value that comes as an approximation from the tangent line, and we would construct a new tangent line that matches the slope of the curve. So what I'm trying to do is I'm trying to get it to match that slope that I just drew on the bottom of those two blue lines, and there it is. Once we get that new curve, then we can use that new curve to make a new tangent line approximation. And the idea is, once again, if we try to match the slope of the function, then what we get is a much more accurate final approximation because we've used much more information about the growth, and I was going to say the growth rate, but the rates of change of this particular solution or this particular differential equation, depending on what we might do. Truthfully, what makes this really powerful, other than the fact that you can see probably just looking at it right here, that it looks like we shrunk the error. And obviously it may not always be this effective, although it's definitely in my favor to endorse it by showing you one that looks this way. There's a little bit of bias built in there. Instead, what I want to point out, that what makes this a little bit more accurate is, of course, you're doing it very carefully and with smaller steps. Like you're basically taking baby steps in this approximation rather than just going whomp and then using an approximation off that single tangent line. A little more information and trying to use the information you have about particular solutions is oftentimes going to reward you a little bit as you dig things in. Now, having said that, obviously the cost is that Euler's method takes a long time. Like that's the one thing that linear approximation has at its advantage. It's like Ricky Bobby, it goes fast. Euler's method, yeah, we have to take a little bit more time. Oftentimes we'd have to do things very carefully and like painstakingly with computations. Obviously that's not going to be our goal here. But the truth is, the power is that Euler's method, like linear approximation, is a numerical solving method. And the reason numerical solving methods, and I guess I should point out that a numerical solving method is one that doesn't require the algebraic solution. It allows you to approximate, basically, in effect. So you're using approximations to get a good, accurate or a maximally accurate representation of a solution. And the reason that these are so useful nowadays is because, of course, computers can do this work for us. Like we don't need to do this by hand the same way we obviously will in the lesson today, and the same way that all sorts of famous people and famous mathematicians once did. Some of our brightest minds working at places like NASA, as you'll see in just a second, were actually literally hand computers, where they actually did these computations one piece at a time, because there was not yet a computer that was capable of doing those massive calculations. So the other cool thing about numerical solving methods is this method, in fact Euler's method, works in situations where there is no solution, where there isn't a way that we can separate variables, where there isn't a way that we can actually solve the differential equation, meaning that you can get an idea about the behavior of a particular curve, or at least solutions to that particular curve, by using these very precise approximations. Obviously, you'd have to be a little more accurate than what we did right here, where we went over by 0.5 every single time and only did 3 tangent lines. If we did that like 10 times, imagine just how much more accurate we would actually be. So, having said that, let me first go ahead and space this out a little bit more. I don't know why I left it so low. I was going to say, let me define Euler's method itself for you. That is the name of the technique, is Euler's method. And I know some people want to say Euler. Well, you learn... You learn that it's Euler pretty fast, but Euler's method is this. So we're going to use iterated, which just means doing the same things over and over and over again, using iterated tangent lines. So meaning we're just going to compute a bunch of different tangent lines, and I'm going to have to put quotes around tangent because, as we said, they're not always going to hit the curve. Notice how this one never touches the curve, neither does this one. So they're not truly tangent lines, they're just pseudo-tangent lines, if you will. We're going to use iterated tangent lines to approximate solutions to differential equations. So kind of a neat thing. So there's what our goal is today. I want you comfortable doing small approximations of Euler's method and understanding what it is, what it does, and how it can be useful, like where its value is going to be to us. Now, of course, our use of Euler's method is not going to be the only place in the world. As I mentioned, like there are people who have used Euler's method to great success. And if you've ever seen the movie Hidden Figures, came out a couple years ago, I want to say 2017, maybe 2016, I might be off by a year. If you've seen that movie, you'll actually probably remember the general story. But in the climax of the movie, while John Glenn is in orbit and they're trying to solve for his path to try to bring him home, one of the computers, like one of the NASA scientists, mathematicians working at NASA, actually comes up with the solution to the problem. And the problem of trying to solve a differential equation that has no algebraic solution. So I'm going to attempt to include the actual video here and play it. We'll see if YouTube allows it through. But in any event, here's a clip from Hidden Figures for your mathematical joy.
Is when the capsule moves from an elliptical orbit to a parabolic orbit. There's no mathematical formula for that. Because we can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe it's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically.
Exactly, because that's going to be part of our problem here, is there are going to be differential equations where, especially for us, because we only kind of know separation of variables, there are going to be differential equations that we just don't have the way to solve. Maybe it won't be as bad a situation as NASA trying to model something that just they made up. They can't necessarily find a model for because they're creating it, but there will be situations where we don't have any ability to work our way through.
Math is always dependable.
Yeah.
Euler's method.
Euler's method?
Yes.
That's ancient.
But it works.
It's ancient? Who cares if it works? Thank you.
It works numerically.
And then she goes to the book, even though I'm pretty confident that she actually knew Euler's method off the top of her head. Aha! So there's our stuff. Obviously, it's going to look a little bit cleaner than that. But at the same time, just so you can kind of see, Euler's method is absolutely the critical tool in a very popular and Best Picture nominated film. So how often can we say that in calculus? Stand Deliver, also a pretty good movie, but not quite the same way. So having said that, what I want to do is I want to demonstrate this technique for you, show you the process, and kind of give you an idea of what's actually happening here. So we'll start with a straightforward example. So we'll try to keep things as clean as possible here. Obviously, at some points, we're going to run into a situation that's going to demand some decimal calculation. Obviously, like when that happens, feel free to grab a calculator here. But let's kick this first one off. So in our first example, it says, use Euler's method with step size 1 to approximate y equals f of 3 for the solution curve to dy dx equals x plus y that passes through 1, 3. So having said what I did, I want to demonstrate an example before I give you kind of the process, simply because I think sometimes having that context really helps. I want you to see what it looks like and kind of hear these words and see what they mean before I tell you kind of here's your step-by-step approach. So let's kick things off. The first thing we want to point out here is there is a little bit of vocabulary that you need before we can even jump in. And the most important thing up here is step size. Basically, like depending on how accurate we want to be, our step size changes. So the definition is as follows. Step size is basically a description of the precision of the movement we're going to make in the x direction, meaning how far we want to move from our original point, or in most cases the previous point, to the secondary point so that we can make our new approximation. So having said that, when we say the step size is 1, that could be a large step size or a small step size depending on how far away the value is that we want to approximate. So having described or having determined what our step size was and telling us it's going to be step size of 1, what that does is it creates what I kind of think of as like a game plan. It tells us exactly what our approach is going to be to perform this approximation. We're going to start at x equals 1. And the reason for that is specifically because it tells us so right here. We're starting at x equals 1. Then from there, we're going to take a step. And that step is going to be 1, size 1. So I'm trying to think of a good way to describe this. We'll take a step of plus 1, and that will take us to our second value. Our second value is obviously going to be 2 because 1 plus 1 is 2. So we're going to do our second approximation at x equals 2. Once we've done that approximation, we want to take and find an approximation for f of 3. So we're going to take another step one more time. We'll again add 1 to our value, and that's going to leave us at x equals 3. So in a sense, because our step is 1 and we want to get to x equals 3, we're going to have to take not just 1 but 2 steps. So it's not going to be like linear approximation where we only do it once. We're going to have to do this twice. So we'll use linear approximation for the first one, then we'll use our tangent line to do a new approximation, and then we'll go forward and finish it off by approximating x equals 3. Having said that, I think my approach here is going to be very organized and really a clean way for us to attack this problem. So I'll do my best to try to keep it there for you. So where are we going to start? We'll start with the point that we have. And as I said, I'll give you the process itself, or if you really want to, you could just fast forward through this video if you want to see it. So I'm going to start with our initial point that we were given right there, 1, 3, and I'll call that x sub 0 and y sub 0, or x naught and y naught, because that's our initial point. That way I'm saying it's our initial x and our initial y. Once we've got that, we can, like usual and like before, use our differential equation dy dx and evaluate it at our ordered pair 1, 3. Oh, you know what, I'll even just put this in there just so it's a little cleaner. We'll evaluate that differential equation x plus y at 1, 3. When we do, that's going to give us our slope as being equal to 1 plus 3, or 4. And actually, I'll go ahead and write it in there, trying to balance looking at what I did this morning and what's here. So we'll set that equal to 4. So what that does is it gives us our new slope. Now that we have our new slope, we can construct our tangent line. So the tangent line, in this case, is going to be y minus 3 equals the slope of 4 times the quantity x minus 1. Now, having said that, we want to approximate specifically, as it says right above, we want to approximate f of 2 because that's 1 unit away. So in our case, what that means is that we can approximate f of 2 by using the tangent line. So our tangent line from before is 4 times the quantity x minus 1, and then I'll add 3 to the end. So if you're wondering where that comes from, just adding 3 to both sides just to move it over, so that way it's explicitly f or y by itself. And then in particular, since we want to know what's happening at 2, I'm going to plug in the value x equals 2. When I do, that's going to give me my approximation that f of 2 is approximately 4 times 1 plus 3, which is 7. So that is my new approximation. Now that I have that, this has created kind of our first approximation. This has taken us right to the middle. Now that we have that value, that f of 2 is approximately 7, we're going to treat that as though it were a point of tangency. So we're going to create a second point, or we're going to create a second move through this process. Instead of having x sub 0 and y sub 0, this is going to be x sub 1 and y sub 1. We're going to plug into our differential equation the same way as before. So dy dx was still, or is still equal to x plus y. This time, though, we're going to calculate the slope at our supposed point of tangency, 2, 7. When we do, that obviously gives us a slope of 2 plus 7, which is equal to 9. So that's our new slope for our tangent line. Because we now have a slope for our tangent line, we can construct the tangent line equation at this point, even though, again, it's not really a tangent line. That'll be y minus 7 times 9, or equals 9 times the quantity x minus 2. And now that we have that, we, of course, made it our goal to try to approximate f of 3. So if we want to calculate an approximation for f of 3, we'll use our tangent line. It's going to be equal to 9 quantity x minus 2, all plus 7. So following the same process we did before. But remember, we said that we want to replace the x value with 3 so we can get an approximation. When we do, we get 9 times 1 plus 7 means that f of 3 is approximately 16. And because our question was only asking us for f of 3, that means that we're done. We found that our approximation for f of 3 is equal to 16. Oops. So having said that, like obviously this process is just kind of the same thing multiple times. If you can do a tangent line approximation, you can use this. It's just you do it once, then you take your result, and then you plug it in, create a new point, and do the exact same process. That's that idea of being iterative that we mentioned before. Each iteration or time running through the process is going to be the same computation. You're just going to be using a new point and constantly shifting around. Now something small you maybe didn't notice here as you looked is this differential equation. If you were thinking like, oh, why don't we just solve it and find the actual value? Well, the reason is this is a non-separable differential equation. And although many of you will end up taking a DE class and finding the way to solve this, it's not actually terrible. It's not that difficult really at all. The truth is we don't have that skill in our skill set, but yet we were able to still find a good approximation or a potential solution on this curve that we don't know how to calculate. So having said that, let me just kind of demonstrate really fast. I think showing you some stuff online would be kind of helpful. My favorite Euler's method demonstration was just inexplicably taken down online, no longer available. I have no idea why. It looked so nice. It was so easy to play with. You could see it really nicely. But just to kind of illustrate, this is one from GeoGebra. I'll link it in the, I'll link it in the video description. But basically we could do the exact same thing we did before. So we started at the point 1, 3, and we wanted the h value to be equal to 1. Let's see what we got. Okay, so right in here is our approximation. Is that what we were looking for? Yes, there it is. So it corresponds to 3, 16. So there it is. Obviously, I don't have the control to be able to move this, but you can kind of see what's happening. In the dark plum purple is the actual solution to this differential equation, and then each of these points represents one of our steps, one of our linear approximation results. So for instance, f of, I think it was 2 is equal to 7, was approximately equal to 7. F of 3 was equal to 16. If we went further up, as you can probably see on the table over here, f of 4 is 35, so we'd be able to get our approximation. I wish I could zoom out. I don't know if it'll let me. Oh, it's letting me zoom out. Yes. There we go. I did not realize I could do this earlier. So there's Euler's method in action. Notice what it looks like is we've got a tangent line, then we break it off and we get to a new tangent line, then we break it off and go to a new tangent line, and slowly we get a decent approximation of the curve. Obviously the error is getting larger as we go, but it's doing a pretty nice job overall. So having said that, that is Euler's method in a nutshell. I promised to give you kind of an approach, like a step-by-step process, so let me do that next, just so we have it, and then we'll do another example before letting you kind of play with it yourself, and talking about accuracy as well. So the process itself, let's look here. To start things off, if you look up Euler's method in most textbooks, they'll give you kind of a complicated explanation. In fact, the first time I ever saw Euler's method, because I don't remember doing it in high school, nor in my college calculus class, which seems unlikely, but at the same time, I'm not sure what happened. You'll often see an expression like this written in. I'm trying to make sure I read it correctly. Nope, n-1. Hey, you know what? I'm here. Clean this up. You often see an expression written like that. So when you look at that, this is meant to just be a tangent line. The only difference is, of course, it emphasizes the idea of iterativity. I don't know if that's even a made-up word, because it's emphasizing that you're using a slope from an old function and an old y value, and you're plugging in a new y value. So starting at n-1 and then going up to n. So having said that, what often follows is then this equation. They'll say that y sub n is equal to n-1 times h plus y sub n-1. And what this is meant to mean is basically it's the same exact thing you see up here, except obviously they've added y sub n-1 to both sides, and they've replaced x sub n minus x sub n-1 with h. The reason is h is just going to represent your step size. And although I emphasize linear approximation as my approach, some people would just point out that this x minus x sub 1 or x minus x sub n is always just going to be equal to step size, because whatever value you plug in is going to be one step away from the previous x value you had. So again, this is just kind of what you'd see if you look it up online. Lots of places discuss it that way. That's not my approach. I take a very kind of methodical approach to it, and it's going to look just like this, which I got to say, it does look fairly nice. I'm pretty happy with what that looks like. So here's my approach, and I'll try to check my stuff. And actually, yeah, Like, I'll try to get this whole approach there for you. Okay, so what is that process going to be? Well, the way we're going to attack it is we're going to follow the same basic procedure we did on the previous problem. We'll focus on creating tangent line equations and plugging into them and then using that to get new slopes before doing the process over and over again. So as it says in step 1, we're going to find the tangent line equation. So just as we did on this first page here, we'll find our tangent line equation, there it is, by plugging into the differential equation to get the slope and constructing that tangent line. Next, we're going to use it to get a new point via linear approximation, meaning basically we'll take advantage of the fact that this tangent line is a good approximation, we'll plug into it, and then we'll be able to see what that value would be if we use linear approximation. Oops. So what that was right here. That was when we went through and we looked at the value itself and found that f of 2 was equal to 7. So we're one step size away, basically. After that, we're going to compute a new slope at the new point. So the way we're going to do that is by plugging into the dE. Our differential equation is going to give us a prescription to tell us what the slope would be at this point were it on the curve. And so then from there, we'll be able to compute our new slope. That's what happened right here. We took the fake point of tangency, the one that was used or found using linear approximation, we plugged it in, and we got our new slope. Once we have our new slope, we can create a new tangent line. And of course, that was our goal at the first place, was to create another tangent line. And then, of course, once we have that new tangent line, we plug into it at the next step, we get a new approximation, and then we just keep doing the same thing over and over again. So that last step says rinse and repeat, which is a good thing in a time when everyone has to wash their hands constantly. Just keep doing the same thing until you've reached the approximation point that you're looking for, until you reach whatever the final x value was you're trying to approximate the value at. And this process is going to work really effectively. It's basically just always using skills that we know. We don't have to memorize some brand new formula. We don't have to memorize some sort of weird relationship. All we're doing is finding tangent lines, plugging into them to get new points, creating new tangent lines for those points, plugging into those tangent lines. We're just doing the same thing over and over again. So that is, in essence, Euler's method. Alrighty, now that you've heard the approach and kind of gotten the rationale around it, let's do a full example so that way you can get a feel for using it now that you have much more command of what's actually happening in it. So here is our example. We're going to use Euler's method with 3 equal steps. So this is a little different. They're telling us how many steps rather than how wide those steps are going to be. And we want to approximate y equals f of 3.5 for the solution curve to, it looks like 3x over y squared that passes through 2, negative 1. So this is one of those problems where it's a very simple problem. We're going to do a couple tangent lines to get there. It's just going to be a little time consuming and some of the numbers are going to get crunchy. So I will take advantage of the fact that I already calculated them out earlier today so that way we have everything ready to go. So to kick things off, let's take a read on some of this stuff because we do have to kind of read a little bit here. So it says that we have 3 equal steps that we're aiming to use here. So we need to take 3 steps. So having said that, if we're going to do this accurately, we need to take into account where we're starting and where we're ending. So in here, we're starting at 2, and we're going to end at 3.5. So if we want to take steps from 3.5 to 2, and we want to take exactly 3 of them, we should be able to see really fast that each of those steps is going to be 0.5. So our step size in this case is going to be 0.5. We just had to do that calculation to get there. Having said that, that means that we have our quick little game plan. Our game plan is going to start at 2. It's going to take us to 2.5. Then we'll go to 3. And then finally, we'll reach 3.5. So that means we've got to do a couple tangent lines to get there. In fact, there's going to be 3 tangent lines, 1 per step. So having said that, let's begin where we started here. We're going to start with the point 2, negative 1. Now again, it's not like you have to call them x sub 0 and y sub 0. I just think it kind of helps get my mind around this idea of doing the same thing over and over again. So if we start there, our slope is going to be equal to our differential equation evaluated at 2, negative 1. When we plug in here, we'll get 3 times 2 over negative 1 squared. That's equal to 6. Now that we have our slope, we can construct our full-fledged tangent line. So that full tangent line is going to be y minus a negative 1 equals 6 times the quantity x minus 2. So having done that, we now have our tangent line. From here, we want to take our tangent line and evaluate it at our first x value, which is going to be 2.5. So we're going to evaluate this at 2.5. When we do, that's going to give us our f value. So f of 2.5 is going to be approximately equal to 6 times the quantity of something minus 2. Ooh, I should use my color. I should keep using color. I'm going to use my color like before. Oops, excuse me. F of 2.5 is going to be 6 times the quantity, x minus 2 minus 1. But as we said, we specifically want to calculate the approximation at 2.5. So we'll plug in 2.5. When we do, that's going to lead us to our approximation being 6 times 0.5 minus 1, which is going to be equal to 2 if memory serves. So that gives us our new approximate y value. So f of 2.5 is approximately 2. So there's our first step. We are here in our little process. Now that we have it, we can move down and do our second iteration. We now are going to use the point 2.5, comma 2 as our x sub 1 and y sub 1. Now that we have new x and y, we're going to plug into the slope equation and get those new values. This will be 3 times 2.5 all over 2 squared, which is going to be equal to, oh shoot, I didn't do it the exact same way. You'll live. You'll be fine. This will be 7.5 divided by 4. 7.5 is the same thing as 15 over 2. So when we divide that by 4, we get 15 over 8. Now that we have our slope, we can construct our tangent line. So y minus 2 is equal to 15 over 8 times x minus 2.5. With us ready with that tangent line, we can now prepare to plug in our next value, which is 0.5 away, which will be at x equals 3. In other words, we want to now calculate f of 3. It's only going to be an approximation, but we have all the tools to do it. So our tangent line is 15 over 8 times quantity x minus 2.5. And then we have to add the 2. So of course we always just bring that 2 back over. Easy thing to miss, I know. As we said though, we want to find the approximation at 3. So we're going to plug in 3 here. When we do, that's going to give us, let's make sure I do this correctly, it's going to be 15 over 8 times 0.5, which is the same thing as 1/2, and then plus 2. So when we combine that, that gets us 15 over 16, and then that's plus 2, which is 32 over 16, which gives us a slope of 47 over, not a slope, that gives us a new y value of 47 over 16. That means that f of 3 is approximately 47 over 16. Maybe not the best value in the world to be working with, but hey, play along, stick along for the ride. So we now have our approximation right here, and we have completed the second step. Granted, we need to do one more, so we've got one final step for us to attack. So with this final step, our ordered pair, our new x and y values, are going to be 3 and the ever lovely 47 over 16. That's going to be x sub 2 and y sub 2. From here, we'll calculate a new slope, and this is kind of where the problem begins. Our slope is going to be 3 times 3, I like that part, divided by 47 over 16 squared. Yeah, not my favorite thing in the world. So thankfully for us, I have this value. I don't have it as a fraction because I felt like nobody really wanted that. So I'm going to call this right here. I'll give you the approximation, or I'll give you the value. It's 1.043005, and then there's more values after that. But for the sake of simplicity, and assuming that you were using a calculator as you were working through this, I'm going to call this the variable value capital M. So this is capital M now we're defining. That will be the slope 3 times 3 over 47/16 squared. So having said that, now that we have it, we'll have our new tangent line as y minus 47 over 16 is equal to capital M, our slope, whatever that number is, times x minus 3. Now that we're doing that though, of course our goal is to evaluate this at x equals 3.5. So our job is now to figure out what's the approximation when we plug in 3.5. So we go through and we do one more move. F of 3.5 is going to be approximately equal to, approximately equal to, we'll have our slope of m times quantity x minus 3, and then plus 47 over 16. And if you feel like this sounds like a broken record, that's because I'm doing the same thing over and over again. That's what iterative calculations are. Just keep doing the same process with new numbers. So at this point, we want to figure it out at 3.5, so we plug in 3.5. When we do, that gives us the value, and let's make sure I say this correctly. this gives us our value. I mean, you can see what the number is. We just put it in the calculator, and it tells us that f of 3.5 is going to be approximately equal to 3.459. And since we were looking for an approximation of f of 3.5, we have it. That value is about 3.459. So, having said that, you can see the process followed exactly what we expected it to and what we said it would. We found a tangent line. That's in the navy blue line here. So we found the tangent line. We plugged in our first value one step away and got our second y value, or our approximation of the new y value. We used that to create a point. We calculated a new slope. We created a new tangent line. Then we plugged in our next value and got a new approximation for the y value. That gave us a new point. We plugged it into the new slope. We used that new slope to create a tangent line. We plugged in the value, and we got our approximation. So that is Euler's method in itself. Tangent line, plug in, new point, tangent line, plug in, rinse, rinse, and repeat. That's it. That is Euler's method. Now, having done all that work, a good question to ask yourself would be, well, did we accomplish anything? Like, if the goal of Euler's method is to be accurate, did we gain accuracy by doing this extra work? Because truthfully, especially with this one, you could see when we got to the maroon line, it just kind of devolved into being really annoying and time-intensive and like calculator-driven. So the question is, did this new method help? Well, to help us reach that point, we could actually check the exact answer, because the differential equation we have here is actually one that we can solve by separation of variables. So I'm going to use this newfound speed-up technique to solve this by separation of variables. This time Okay, I returned at this point. So our question is accuracy. How accurate have we been? Did the extra work of Euler's method give us a better approximation of our answer than linear approximation would have? Well, let's go back and actually do some quick remembering. Remember at the very beginning, we had this same very problem, and we used linear approximation, and we got that f of 3.5 was equal to 8. So that was our first one. So using linear approximation, we have f of 3.5 is approximately equal to 8. What that means is if we want to calculate our percent error, we're going to do that pretty simply. We're going to take 8 minus the approximate value, 3.3057445, ... and then we'll divide by that correct answer, which was 3.3057445. It's kind of annoying. I'm sorry that it was annoying for me to put it in there. Oh, and I can't. There it is. Okay, so we'll do our quick calculation. And if we use a calculator, pretend I'm punching a calculator in right now rather than just looking at my notes, this is an error, a percent error, of 142.003%. So, maybe it's okay. Like, we'll find out. But, yeah, it doesn't necessarily look like the best calculation in the history of the world, but it is what it is. So we'll start there. So linear approximation by itself gave us an error of 142%. Let's take a look at Euler's method. So Euler's method is going to use a lot of the same ingredients. The only difference is our approximation was right here. F of 3.5 is about 3.459. 3.459. So when we set this one up, 3.459 minus that value, and here I'm going to do what I should have done before. Since I already did the calculations, I can do that. Boom. In our denominator, we'll have that same value, 3.3057. Let's see, when we calculate the percent error on this one, that gives us a percent error of 4.636%. So, I'm no expert in percent error, but if someone gives me the option when measuring something important to me of either having 142% error or 4.6% error, at a little extra cost, I mean, there's a little extra cost of doing some work and popping out our calculator, I'm going to take the one that's 4%. Like, that's just a huge improvement for what was just a little bit of calculation, like a 5-minute calculation. That in many cases isn't even that hard. It just happened that we reached a point and we're using an approximation that made things kind of unruly. So the truth is, if you wondered why we use Euler's method rather than just straight linear approximation, it's because it's simply better. Now that doesn't mean that suddenly we're going to get this tiny error when we do two approximations, and there are going to be differential equations where the growth rate just doesn't model as well and we get really inaccurate estimates, but at the same time those estimates are almost always far superior to a linear approximation estimate. In fact, I would say they're always a better approximation. They just might not be fruitful in giving us a really accurate number for a particular solution. So just so you're aware, there is kind of a nice little moment to celebrate just how accurate Euler's method is at calculating approximations, especially compared to our old friend, the trusty and reliable but not necessarily that accurate friend, linear approximation. Okay, having hopefully convinced you that this skill is valuable, it would normally be about time for the try it. I just want to do one more example. Obviously, if you prefer to skip ahead to the try it, go for it. But I did want to do one more just because I've seen this question asked this way before, and I think it feels sort of unsettling the first time you do it. So I think it would be valuable for me to go through this problem rather than treat it as part of the try it. So I kind of adjusted what my plans were from this morning and kept this in there after kind of thinking about it a second time. So in our situation here, it says you've got a table above. In fact, this looks kind of small. I'm not sure. Okay, so it says the table above gives values of g prime for selected values of x. So we're looking at the derivative of function g. If g of 4 equals -3, what is the approximation of g of 5.8 using Euler's method with 3 equal steps, starting at x equals 4? So we're trying to approximate a value using Euler's method, but interestingly enough here, we're not given a differential equation. So there's something that's going to feel a little bit different about this particular problem. I think the best way to get into it, though, is just to start off just like you would any other problem. Write a tangent line once and then see what happens. So let's kick that off. So first of all, our ordered pair that we have comes from our initial condition. We're given that one tiny condition that g of 4 equals -3, which means we have the point 4, -3. That's going to be our x sub 0 and y sub 0. From there, we're going to be able to calculate the slope, but if we want to think about this right, our slope is not going to be what we get when we plug in both x and y. It's going to be just our derivative at 4. So in other words, the slope is g prime of 4. And according to our picture up there, let me just make sure I'm reading this right, I am, g prime of 4 is equal to 5. There it is in our problem. Once we have that value, we can write our tangent line equation. So it's going to be y plus 3 equals 5 times quantity x minus 4. And once we have that equation in place, we can plug in x equals our next value and move on from there. The problem is we don't know what that next value is because we haven't calculated out what our step size is. Right now we just know we need 3 equal steps. So to calculate that step size, which I'm going to call h for the moment, just using the old method of doing it, our step size is going to be 5.8 minus our initial value, which is 4, and then divided by 3 because we have 3 steps. That's 1.8 divided by 3, which is equal to 0.6. So in other words, if we're going to use 0.6 as our step size, we'll start at 4, we'll move to 4.6, we'll move to 5.2, and then we'll finally wrap up at 5.8. So really it's just kind of that standard way of getting there. We just had to find our step size. So in other words, we already have 4, so we're going to calculate what happens at 4.6. We're going to plug into our tangent line, and we're going to get our approximation. So g of 4.6 is going to be approximately equal to the value in here. So it's going to be 5 times quantity x minus 4 minus 3. But as we said, we want to approximate it at 4.6. So I'm going to go ahead and plug in 4.6. When I do, that's going to give me my new value. I keep wanting to say f. I want g of 4.6 is going to be approximately equal to, it looks like 0.6 times 5, which is 3, minus 3, which is equal to 0. So interestingly enough, we get 0 out as our value. But that's no matter. We're now at the point 4.6, comma 0. That's going to be x sub 1 and y sub 1. So from here, we'll calculate our new slope. Well, our new slope, since there's no differential equation to plug into, is just going to be equal to g prime of the x value, which is g prime of 4.6. According to the table, g prime of 4.6 is equal to 6. That means we can construct our tangent line. Y plus 0 is equal to, it looks like 6 times x minus 4.6. So there is our tangent line equation. We're now going to plug in our x value, which is going to be x equals 5.2. So digging in here, our next thing, g of 5.2 is going to be approximately equal to let's see, according to this, it's going to be 6 times quantity x minus 4.6. And then, of course, it's minus 0, but we don't really have to include that. But we want specifically the value at 5.2. So I'll plug that in. When I do, I'm going to get that this is equal to 6 times 0.6, which is equal to 3.6. Memory serves, let me make sure. Yes, it does. So what that does is it now gives us our new y value. So having done so, we can now say that our point is 5.2, 3.6. Then we just do it one more time. So basically we're right here. We want to get to here, so we've got one last step to finish. So calculate our slope as we have each time. That's going to be g prime of the x value, which is 5.2. And according to our problem up here, 5.2 slope is equal to 7. So that gives us our new tangent line of y minus 3.6 is equal to 7 times the quantity x minus 5.2. Now that we have it, our goal was to figure out what x is equal, or what happens at 5.8, or what our approximation with Euler's method would be at 5.8. So we're going to plug that in. In other words, we're going to calculate an approximation for g of 5.8. That approximation is going to be equal to 7 times the quantity, x minus 5.2, and then plus 3.6. But we already established that our goal here was to approximate at 5.8. So with that in mind, we're going to be able to take that and set it equal to 7 times 0.6 plus 3.6. That's going to be equal to 4.2 plus 3.6, which is going to lead us to our final approximation. In other words, g of 5.8 is equal to 7.8. Boom. And there it is. We've wrapped this up. We found our approximation. The thing that was a little different here, and is probably only unsettling until you saw one line of it, but playing along for the moment, the thing that was unsettling was we weren't using a differential equation the traditional way. We had an explicit formula for slope as a function of x, but once we took that into account, it just kind of saved us a process. We were just reading out of a table instead of doing the traditional work. So there is our approximation using Euler's method. Interestingly enough, this is a numerical solution to a problem or a function that is presented numerically. So it's like super numerical, if that's kind of your thing. Having said that, that brings us to the end of this lesson. Like, we now have enough information. You've done the entire process of Euler's method. You've gotten to see it in action. You've gotten to see kind of where it comes from and why it's beneficial. We've looked at some applets. We've watched a clip from a movie, I think from Disney. I have to check to make sure that's the production company. And we even got to work through a couple problems that were a problem that was presented numerically, and even analyze the accuracy of an estimate. So having said that, I leave you with the final bit to kind of check your ability to do that. I'd say both of these problems are fairly straightforward examples. The first one, as it says, calculator's okay. The computations get unruly pretty fast. I wasn't able to come up with a clean one right off the top of my head, especially because I want to save some to write a new problem set for this one. But at the same time, it's doable. It's using the process and getting comfortable with the mechanics of executing Euler's method. The second one, I think, is a much cleaner problem, but it does ask you to find the percent error, so you will have to solve the differential equation using separation of variables. But I made it one that's fairly clean and easy to work with. So you'll be able to just kind of see. If you want to, you can compare it to linear approximation, but it's just to let you kind of practice that computation as well. So having said that, that completes the final lesson of Calculus BC. As far as new material, don't get excited. It's just the end of that. So this is the last bit of new information. There are a few other topics that I might polish off or throw in there if I feel like I've got good enough time to get it in there. There are a few things that we didn't explicitly hit in Calculus AB at any point, but that I think you can probably figure out. But if we have the opportunity, I'll try to find some time to slide that in as well. With that in mind, though, of course, with this try it, please do check your answer in the Google Drive or wherever it is that the try-its are being posted. Like, if you want to take a look at the work, I'll make sure to finish those up and get them up there soon. But in any event, obviously, I will be back to you to talk about things like warm-up quizzes, standard quizzes, excuse me, mock test, preparation for the AP exam, all that good stuff. Details are just coming out. They'll soon have some sample exam question type things to look at, although I think I have an idea of what they're going to look like. And I'll, of course, start sharing that stuff with you and use video as much as possible to help out. So having said that, thank you for watching this video, as well as I think 13 that preceded it, or 12 that preceded it. I hope that they've been moderately entertaining, although I know sometimes I'm not as funny as other times. It's different because it's way less fun without having you in front of me. Also, with the whole shelter-in-place pandemic thing, it doesn't necessarily exude happy joy. But at the same time, it's definitely been a good experience for me, finding some way to connect with you, even if it's just through things like Euler's method. But yeah, obviously I hope these are a useful tool to you, and hopefully you've been able to learn some bit of the material that you wouldn't have gotten to otherwise without them. So having said all that, let me just say one more time, thank you so much for being a part of this. I'm obviously going to look forward to working with you more as we prepare for the AP exam at one of the 2 dates that are upcoming. But until that time starts, and just know that I really appreciate all the work that you're doing. I miss you. I wish that we were in class together, even if sometimes the class could get loud, or sometimes people would get angry at Megan for problems involving vases. I don't know, I still don't understand that one. But obviously I'd just rather be there. But since we're not, hopefully this has been a decent enough approximation of and a good tool for your learning. So as always, thank you for watching, and I really hope you're well, and I look forward to communicating with you again, talking to you again, and at some point probably during the summer, seeing you again. Thank you. Have a great night, everyone.